Motion graphs. First, I want to clarify some terminology. Displacement. This is given the symbol s and is the distance travelled in a given direction. It is a vector quantity. Velocity. This is given the symbol v and is the rate of change of displacement. This is the speed in a given direction and is also a vector quantity. We can write that v, velocity, is equal to delta s over delta t, where delta s is the change in displacement and delta t is the change in time. So this basically says in symbol form that the velocity equals the rate of change of displacement, as given by this statement. It's important to note that we cannot split the delta from the s or the t, so in rearranging the equation you would have to move delta s as 1 unit or delta t as 1 unit. Now let's look at a displacement against time graph. The first quantity stated, displacement, goes on the y-axis and we must give the units, in this case meters. The second quantity goes on the x-axis, again with units. This simple journey here just shows us that at this time we had this displacement. At this time we had the same displacement here, and so on. So with this object the displacement is not changing with time and the object is stationary. Another displacement time graph, but this time with a straight line sloping upwards. This shows us that displacement is changing at a constant rate. This is a constant velocity. If we mark a change in displacement here, delta s, over a certain time interval, delta t, if we work out the gradient, that would be delta s over delta t. But we said earlier that delta s over delta t equals the velocity v. So the gradient of a displacement time graph gives us velocity. Here is another displacement time graph, this time with a line sloping upwards. If we were to work out the gradient at this point, and then the gradient at this point, we'd find that the gradient has increased. Here the gradient has increased further. As gradient equals velocity, if the gradient is increasing, velocity must be increasing. This is acceleration. In this case, the gradient of the line is decreasing, therefore the velocity is decreasing. We could call this deceleration, but strictly speaking, at A level we ought to call it negative acceleration. So, when the gradient is decreasing, velocity is decreasing, and we have negative acceleration. So, we've looked at displacement time graphs. Now let's look at a velocity time graph. So in this case, velocity, again with units, meters per second, on the y-axis, time in seconds on the x-axis. If we start again with a straight horizontal line, this means that the velocity at this time is this particular value. At this time, the velocity is the same value as it is here and here. So the velocity is not changing. This is a constant velocity. Don't forget, with a displacement time graph, this shape of graph meant a stationary object. Let's just step back from the graphs for a minute and look at what is meant by acceleration. Well, acceleration is given the symbol a and is the rate of change of velocity. If velocity is increasing, the rate of change will be positive and acceleration will be positive. If velocity is decreasing, the rate of change will be negative and we have negative acceleration. We can write this in symbols as acceleration a is equal to change in velocity, or delta v, over change in time, delta t. again we can't split the deltas from the v or the t. So here's another velocity time graph, this time with a straight line sloping upwards. This straight line shows that the velocity is changing at a constant rate. If we work out the gradient as we did before, this value here will now be delta v, or change in velocity. This value here, delta t, change in time. The gradient is delta v over delta t, which, as we said before, is the acceleration a. So the gradient of a velocity time graph gives acceleration. With this velocity time graph, the gradient is increasing, so the acceleration is increasing. And with this one, the gradient is decreasing, so the acceleration is decreasing. But here, the object is going at a greater velocity than it was here. Here it is still going at a greater velocity than it was here. So the velocity is still increasing, just that the rate of change of velocity, or acceleration, is decreasing. Now back to a displacement against time graph. Note I've again used the symbol S for displacement and T for time. And let's have a more complicated journey, something like this. I'm going to label the significant points as A, B, C, D and E, and then looking at the journey from A to B here, it is a straight line sloping upwards. That is a constant change in displacement, which is a constant velocity. From B to C, the horizontal line shows us displacement doesn't change over this interval, so from B to C the object is stationary. From C to D we again have a straight line sloping upwards, but with a larger gradient than from A to B. So it again is a constant velocity, but that value is greater than it was from A to B. And going from D to E the gradient is reducing, so the velocity is reducing, which again is negative acceleration. To really get to grips with the differences between displacement time graphs and velocity time graphs, I've reproduced the same shape of graph, but this time made it a velocity against time graph. From A to B we have the straight line sloping upwards, which is a constant change of velocity, or a constant acceleration. From B to C, the velocity does not change, so the object is at a constant velocity. From C to D we have this steep straight line upwards, which is a constant acceleration, but a greater value than it was from A to B. D to E now, the acceleration is reducing, but don't forget the object is still getting faster, just at a lower rate. So we've found that the gradient of a displacement time graph gives velocity, and the gradient of a velocity time graph gives acceleration. Let's look now at what the area of a velocity time graph gives us. If we wanted to work out the area of this blue rectangle, we would multiply the width, which in this case is going to be a velocity v, by the length, which in this case will be a time t. So the area is equal to a velocity multiplied by a time. But velocity times time is simply displacement. So the area of a velocity time graph gives us displacement. If we have a velocity time graph something like this, we can just work out the area of the triangle. And remember, area of a triangle is equal to half times the base times the height. A more complicated shape, something like this, can normally be split into a series of triangles and rectangles, and just worked out separately. Summarizing what we've found so far. The gradient of a displacement time graph gives velocity. The gradient of a velocity time graph gives acceleration. and the area under a velocity time graph gives displacement. Let's look at an example. For the journey represented below, we're asked to calculate the displacement in the first 4 seconds and find the acceleration at 6 seconds. Well, displacement is area under a velocity time graph, so in this case we want to find the area of this shape here, which we can easily find the area of this rectangle as 2 times 10. We have 2 seconds here times 10 meters per second, which gives a displacement of 20 meters. This triangle has an area of half base times height, which is half, times 2 times 10, which is 10 meters. So we have a total displacement of 30 meters. To find the acceleration at 6 seconds, we need to find the gradient of the velocity time graph at 6 seconds. So to pinpoint just where we are on this line, I'll draw a line up from the 6 seconds and then draw a tangent to the line at this point, getting it as close as possible to the gradient of the line at the 6 second mark. If I now draw a line for reference up here and across to the y-axis, I find that this line here has a length of 18 meters per second, and this line here, the base of my gradient triangle, has a length of 4 seconds. Now acceleration is delta v over delta t, which in this case is 18 meters per second over 4 seconds, which gives an acceleration of 4.5 meters per second squared.